soon. All right, how would we say there is no rain soon? Well, not R, right? If R is there is rain soon, not R is, it's not the case that there is rain soon.
Then
So if R,
D.
then D, right? So that's one. All right, what about the second one? What about this? What do you think?
D arrow F.
Yeah. So if D, then what?
F.
Not quite. Right? F is there will be food for winter. So how will we say there will not be food for winter?
Not F.
Not F. Exactly. All right. Well, the crops will die. D is the crops will die. So then the crops will not die.
Not D.
Not D. And therefore, there will be rain soon.
Not R, not D. Not R, arrows D.
Well, all we need to say is just this: there will be rain soon.
R.
So it's just R. Yeah. Right. So this is the symbolization, right? So you take it one statement at a time, right? Roughly, it's usually one sentence at a time. If there is no rain soon, the crops will die. Okay, so if not R, then D. If the crops die, then there will be no food for the winter. If D, then not F. The crops will not die, not D. Therefore, there will be rain soon, or there is rain soon, which is just R. Right. So this would be a symbolization of this argument. Right? Assuming that R stands for there's rain soon, D is the crops will die, and F, there will be food for the winter. So there are two things to notice here, or just to keep in mind. Your letters, right? So the letters you pick, it doesn't matter what letters you pick, as long as you're consistent, you use it for the same statement. But they should always stand for positive statements. Because you can always, the negation you can always express by using negation. So letters always stand for positive statements. So when you're thinking about what, let's say, what R stands for, there shouldn't be a not in the statement that you're symbolizing, right? If there's a not in there, or couldn't, wouldn't, shouldn't, right, some kind of negation, then it's not simple, right? Because a negation is complex. So a letter always stands for a positive statement. And then anything negative you express by adding in a negation. What was the second thing to notice? The second thing to notice, well, it's sort of related, right? When you see negations in there, there is no rain, there is no food, it's not the case, you should immediately say, okay, if something negative is being expressed, a negation is involved, right? That's almost 100% true. I mean, I can't think of an example where we would use a word like no or not, but we're really expressing something positive. There's probably something. English is a weird language, and right. But if you see a negation in a statement, then it's a good bet that there'll be a negation involved in the symbolization. Okay, so the end is finally in sight. The end of this is finally in sight, right? What do you have to do to figure out whether an argument is valid or invalid? Well, you take the argument, you symbolize it, and you do a truth tree, right? That's where it all comes together. So this is, sort of one of the steps along the way. And speaking of truth trees, let's go back to the torture chamber and try it out. All right, so now I'm going to do, right. So we had some homework. Let me bring it up briefly. And then I'm going to get the whiteboard going. What do we have? Where is it? You think I would learn to just have fewer windows open? But no. Okay. All right, so we had three, what was it, three? Number 3, number 4, and number 6? I've already forgotten. Well, let's just look it up. 3, 4, and 6. How did you guys get on with that? Yeah, 3, 4, and 6. Number 3, number 4, and number 6. Good, bad? Not great. Did you do it? I suppose there's maybe another question to ask. All right. So, what should we do? Let's go through it. Now, what I recommend at this point is, right, on your laptop, open up the slides with the rules. Let's see, where are they? Tree rules? Nope. So, right, have one of these slides, either slide 134 or 135 open to you so that you can refer to it all the time, right? I'm going to do this one, the one slide summary. And second, I recommend highly that you write down, right, that you copy along as we go. So I'll work through it, and you should write down, right, what I'm doing. That's not just a sort of rote, try not to do it just by rote. The point is that it's, part of this is kind of muscle memory. Sort of gray muscle memory. Taking it step by step is a good way to see what's going on, and doing it, right? Watching is one thing, doing it is another. It's easy to say, to be an armchair quarterback, right? That's fine, but actually getting out there and doing it is a whole different ballgame. All right. So we had the first one. There we are. All right, so I'm going to write up, what was it? Number 3. So number 3 was P or Q, P, therefore Q. All right. So this is we want to see whether this, what just happened? We want to see whether this is valid or not. Okay. So, how do we start this tree? You remember what's the first thing we do?
Do you write it down with T, and then F?
Yes, but what do we write down?
T, P, T, P. Right?
Uh,
Yeah.
So we start off. So the first thing you do is you write down the premises and the conclusion. So you rewrite the argument, basically. You copy down whatever it is the argument is going to be. So P or Q, P, Q. Step one. And the second step is you say that the premises are true. The premises are true, and the conclusion is false. You always begin a tree like this. Sorry, give me just a second, because... all right. Can you hear me better now? Or...
It's fine.
Okay. You just changed microphones. Maybe that's the drawback of having two computers going at the same time. All right. So this is how we start. So 1, 2, 3. All right. You take the premises and the conclusion, you copy the argument, you say the premises are true and the conclusion is false, right? So we want to see what happens when we say that the premises are true and the conclusion is false. Can we make it work? Does it not work? And then you start applying the rules to all of the complex statements that you have in the tree. All right, well, 2 is a simple statement. 3 is a simple statement, nothing to do there. So only number 1 is we can apply a rule to. And number 1 is a true disjunction. And the rule for that is if you have a true disjunction on your tree, then you create 2 new branches, and on one branch you say P is true, and on the other branch you say Q is true, right? So the true disjunction rule says if P or Q is true, then either P is true or Q is true, right? The branching says there are 2 alternatives, right? One or the other is true, maybe both, but there are 2 possibilities. All right, so we say P is true and Q is true, right? This would be 4 and 5. All right, and we're done with that. Okay, and now we've finished growing the tree. There's nothing else we can do. There are no more complex statements, so we're done, right? Once you've applied a rule to every complex statement, you're finished. So then one of the nice things about this technique is that it finishes, right? It's always finite. At some point, there's nothing left to do. Okay, now we have to examine the tree, and we have to look on each branch and figure out if there's a statement that's both true and false on that branch. So let's take this branch, right? So this is one branch. Oops, I don't know. All right, is there a statement that's both true and false on this branch?
No.
No. Right? There's no statement that is both true and false on the branch. Okay, so this branch, right, is called open. There's no contradiction on that branch. Okay? Fine. What about the other branch? This one. Is there a statement that is both true and false on this branch?
Yes.
Yeah, right? It's 5 and 3. So 3 says Q is false, and 5 says Q is true. Okay, that's a contradiction. So this branch is closed. Okay. What does this mean? Can you remember what is... So now we've examined the whole tree. what does the tree tell us? We have one open branch and one closed branch. What do we learn from that?
Does that mean it's invalid?
Yes, it does. It means that it is invalid, right? So it means that this argument here is not valid. It means that it is possible for this argument to have true premises and a false conclusion, and the red branch shows us this. The red branch demonstrates that that can happen. If you assume that the premises are true and the conclusion is false, right? So if you, come on, Zoom. If you assume this, right, this combination of truth values, then the branch in red shows you that that is possible. When you assume that, you don't get a contradiction, right? So in particular, when P is a true statement and Q is a false statement, the premise is true, the second premise is true, the conclusion is false. There's no, right? That is a possible combination of truth values. There's no contradiction. So the assumption that the argument is invalid works. So it's an invalid argument, right? We've in effect, what the tree does is it assumes, you start with the assumption that the argument is invalid, and an open branch demonstrates that that assumption works, that you can make that happen. So, right, it's kind of like being in a court of law. You accuse the argument of being invalid, and an open branch proves that the argument is guilty of being invalid. If all of the branches are closed, then there's no case to be made against the argument. Okay, any questions about this? All right. Let's do the next one. So the next one was 3, 4. All right, so 4 was if P then Q, not P, therefore Q. Therefore Q. All right. So that's what we want to figure out. All right. So first things first, what do we write down?
If P, then Q.
If P, then Q. Yeah. And then
you could put the T for P.
yeah.
It's true. Then we can put if not P, then Q. So we will put the Q.
Where do we put not P? Where do we put Q?
So wait, it would be P then Q. If not, then the P would go there.
Mm-hmm.
And then you would write the line and then Q.
Yep. Yeah. You don't need to write the line, but I mean you can.
Okay.
That's fine. Okay. And then we say that the premises are true and the conclusion is false. So you take the argument you want to examine, you rewrite it, right? You just copy it the way it's laid out, and then you say the premises are true and the conclusion is false. So T for the premises, false for the conclusion. Okay. And then you start applying the rules. All right, so this time we have 2 statements that are complex. So we have 2 things we can apply rules to. You can apply the rules in any order you like. There's no, it's not necessary like to worry about it. So you can do it whichever way you like. All right. Let's do it with number one. Let's start with number one, because it gives us a chance to talk about the conditional rule, which I think we touched on briefly, but is always worth going over. All right, so the true conditional rule says if you have a statement, a true conditional on your tree, right? So true if X then Y, then you start two new branches, and on one branch you say that the antecedent is false, right? So, and on the other branch you say that the consequent is true, right? So what does this rule say? It says if X then Y is true, then either X is false or Y is true, right? Which is just the truth conditions for a conditional. A conditional is true when either the antecedent is false, right? Or
I'm sorry, Professor. Could you just
Yeah.
back up a little bit? Just run that back for me one more time, please.
so if a conditional is true, right, either its antecedent is false or its consequent is true. That's when a conditional statement is true. Under what conditions is a conditional statement true? There are two possibilities. Either the antecedent is false or the consequent is true, right? So you can go back to slide number either slide number 108 or slide 116, right? They have the appropriate the truth conditions for each of the statements, right? So what this rule tells us is it's another way of expressing that condition. A conditional statement is true. If a conditional statement is true, then either the antecedent is false or the consequent is true. So starting with applying this rule from number one, what would we write down? What should we write down?
P is false and Q is true.
That's right. P is false on one side, Q is true on the other side. Yep. So we've applied the rule to number one, right? So if we assume that if P then Q, P implies Q is true, well, what does that mean? It means either P is false or the Q is true. There are two possibilities. All right, so we're done with that. Next is number two. All right, and we have a true negation, right? And the rule for a true negation is if you have true not X, then you can write down false X, right? If not X is true, then X is false. Okay, so if we have not P up here, what should we write down?
P is false.
Yeah, and where do we write that P is false?
Under the
So let me
P
tell
is
you
false?
yes, but also somewhere else. So the rules work like this. You write down what the rule tells you at the end of every branch that the statement you're working on is on, right? So number two is on two branches. It's on the branch that ends with 4 and it's on the branch that ends with 5. So you write down what the rule tells you at the end of every branch that it's on. So you write down false P at the end of this branch, and you write down false P at the end of this branch as well, because number 2, right, is on both of these branches. So you write down what the rule tells you at the end of all of the branches. All right, and we're done with that. And that's true of every rule. You add whatever the rule tells you to the bottom of every branch that it's on. Okay. Right, and sometimes you do get some redundant information. Okay, sometimes you get some redundant information. That's fine. All right, so there are no more complex statements, so we're finished. No more rules to apply, nothing else to do. Now we examine the tree, and we go branch by branch. All right, so one branch, let's check to see if the branch is open or closed. Does it have a contradiction on it or not? Okay, so on the red branch, is there a statement that's both true and false? Right, we have no. We have P is false, Q is false, not P is true. If P, then Q is true. All right, there is no statement that has both a T next to it and somewhere else has an F next to it. Right, there's no contradiction, so this is open. Okay. What about this branch? Is there a statement that's both true and false on this branch?
Yes, Q.
Yeah, right. So 3 and 5. All right, so this branch is closed. Okay, we've gone through the tree. There is at least one open branch on the tree. So what have we learned from this tree? What does the open branch tell us?
That the statement is valid.
It tells us that it's possible for this combination of truth values to exist, right? It is possible to have true premises and a false conclusion, and there's no contradiction. So that assumption, when we accuse the argument of being invalid, you have true premises and a false conclusion, it turns out that we can make that case. So what it shows us is that the argument is invalid. Right? It can have true premises and a false conclusion. So the thing to remember is this: if there is at least one open branch, then the argument is invalid. Right? You just need one. If there's one open branch, then the argument is invalid. It's possible to make the case that it has true premises and a false conclusion. Right? And that means it's invalid. So valid means that all of the branches are closed, that there is no open branch at all. That's when an argument is valid. So this argument has one open branch, at least one, so it's not valid. Okay, this argument is not valid. If P then Q, not P, Therefore Q, right? That's this is the one that's called denying the antecedent. If you go back to chapter 4 and look at the different forms of argument that we went through, some of the common forms, this is one of the common invalid forms. Okay. No. Uh-oh. I just dismissed somehow got rid of the little control panel that lets me do stuff. What do I do? Let me press that. Okay. Any questions about this one? All right. And then we had 3, 4, 6. All right, 3, 4, 6. So 6 was this. If P then Q. What? If Q then R, therefore Q. Okay, so how do we start?
You rewrite the argument.
Yep. So we just rewrite the argument. If P then Q, if Q then R, therefore Q. And the line is optional. And we say that the premises are true and the conclusion is false. You always start the tree like that. Okay. And now we have two true conditionals. So, right, the rule is, right, if a conditional is true, then we say the antecedent is false and the consequent is true. This is the rule for the true condition. Okay, so we can start with number 1 or we can start with number 2. All right, well, start at the beginning. Start with number 1. All right, so from number 1, right, we would start 2 new branches, and what do we put on each branch?
You're gonna put FP and TQ.
Yep, FP on, FP.
And that's only for the true conditionals.
Yes, that's right. FP and true Q. Yep. Okay. Now the next thing we have is true if Q then R. Okay. What do we write down here?
Isn't it the same thing?
Yes. But where do we write down the result? Right? So you add what the rule tells you to the bottom of every branch that the statement is on. So number 2 is on 2 branches, right? Number 2 is on the branch that ends in 4, and it's also on the branch that ends in 5. So you add what the rule tells you to the bottom of each branch. All right, so
you would make the roof looking thing under each one.
That's right. That's right. So, right, we start 2 new branches at the bottom of every branch that the thing is on. So, number 2, since it's on the branch that ends with 4, right, we would have to add that false Q and true R. but also on the branch that ends with 5, because we're applying the rule to 2, which is on both branches, and so you add it to the end of each branch. That's always true. That happens for every application of the rule, right? So this part of the tree, right? Where did 4 and 5 come from? They came from number 1, right? And now we have 6, 7, 8, and 9. This whole part of the tree came from number 2, right? So in that this whole bit came from one application of the rule, right? Because we have to apply it 2 times. So you get branching, right? I mean, trees grow branches. That can happen. You can have 4 branches, you can have 8, you can have 16, you can have 32, right? If you have very complex statements, you can get very big trees. But that's just the way it goes. So don't be afraid of adding lots of branches. If that's what the rule tells you, then that's what you should do. Okay, we're done with this. And there's nothing left on this tree that we can apply rule to, right? We've none of the statements 3 downwards are complex, so there's nothing to do with them. So now we have to examine each branch and see whether there's a statement that's both true and false on the branch. All right, so right, you can start with whichever branches you like. Let's start with the leftmost branch. Is there a statement that's both true and false on the red branch?
No.
No. Okay, so this branch is open. All right. Yep, that happens. All right. Next branch. So the next branch is, right, this yellow one. All right. Is there any statement that's true and false on this branch, the yellow branch?
No.
No? All right, so also open. Okay. How about what did I do wrong here? Nothing. On the ice blue branch, is there a statement that's both true and false?
The Q.
Yeah, so 8 and 5, there's a contradiction there. And what about on the light purple branch?
Yes.
Yep. So 3 and 5, right? True Q, false Q. Okay. So we have a tree that has 2 open branches and 2 closed branches. What can we conclude from that?
That it's invalid.
It's invalid, right? It is possible for the premises to be true and the conclusion false, right? We made this assumption, and these 2 branches, the 2 open branches, show us that that assumption works out. And it works out under 2 possibilities. So when Q is a false statement, P is a false statement, and Q is a false statement, then the premises will be true and the conclusion is false. Moreover, the yellow branch tells us that when Q is false, P is false, and R is true, the premises will be true and the conclusion is false. So it's possible. It can happen. So this is an invalid argument. Yep. It does occasionally happen. All right. Any questions about this?
I'm good.
Okay. All right. So those were the ones that were for homework. Let's now try another one. Okay, and this one, oh yeah, there's a good one. This is also from the book, or from the document you have on Blackboard. But this is a good one that will also demonstrate a couple of important points. All right, so we have if P then Q, therefore if P then P and Q. All right. All right, so if P then Q is the premise, if P then P and Q is the conclusion. All right, so how do we start? We rewrite the argument. If P then Q, and the conclusion, if P then P and Q. And we say the premises are true and the conclusion is false. Okay. So this is how we start the tree for this. Okay, so now we have two complex statements. We have number 1 and number 2. All right, so, and they're both conditionals. Okay, so to refresh our memories, the true conditional rule says if you have a true conditional, you write down that you create 2 new branches, you say the antecedent is false and the consequent is true. Okay, the false conditional rule says if you have a false conditional, then you write down that the antecedent is true and the consequent is false. Right? So both. Right? So what does this rule say? It says if X implies Y is false, then X is true and Y is false. Right? When is a conditional false? It's only false when the antecedent is true and the consequent is false, when both of those things happen. Right? So a conditional says that Y follows from X. Well, when is it false that Y follows from X? Well, when X happens and Y doesn't happen, right? When Y doesn't follow. So this is the false conditional rule. All right, so now we have 2 conditionals. Which one should we start with? Take your pick, right? It doesn't matter what order you go in. Let's start with number 1. We've had more practice with that one. All right, so from number 1, right, we create 2 new branches and we say that P is false and Q is true. So let's say that's 3, and that's 4. All right, we're done with that. Okay, now what do we do with number 2? What do you think? Right? You add what the rule tells you to the bottom of every branch that the statement is on. So 2 is on both of these branches.
So do we create 3 branches on each one?
You just continue each of the branches. Right? So 2 is a false conditional. That's this one. And the rule says if you have a false conditional on the branch, then at the end of the branch, you write that the antecedent is true and the consequent is false. All right, so from number 2, at the end of this branch, at the end of the branch ending in 3, you would write that P is true, and the consequent is P and Q, so you would say P and Q is false. And you do the same on the other branch. So P is true, and P and Q is false, right? So these 2 here came from number 2, right? And you cross it off because once you apply a rule to something, you never come back to it. So we're done with that. Okay, so that's where these came from. So these are, let's call these 5, 6, 7, and 8. Okay. So, right, if a statement is on more than one branch, you add what the rule tells you to the end of every branch that it's on. So since 2 is on both of these branches, you just do what the rule says at the bottom of each. So sometimes you may end up having to add something twice, 4 times, 8 times, 16 times, depending on your tree. Yeah, there's repetition. That happens, and that's fine. That's exactly how it should work. Okay, so we're done with that, but we're not finished with the tree, right? What's left?
Number 6 and 8.
6 and 8, that's right. 6 and 8 are still complex statements, and so we have to apply rules to them too, right? So sometimes in your premises, right, the parts of the premises are themselves complex, and then once you break them up, you apply the rule, you still have something complex left over, you have to apply a rule to that too. So now we have 2 false conjunctions. Okay, and let's, what's the rule for a false conjunction? The rule is, so if we have false X and Y, then you create 2 new branches, and on one you say X is false, and on the other you say Y is false. Right? So the false conjunction rule says if X and Y is false, then either X is false or Y is false. There are two possibilities for a conjunction being false, right? At least one of its parts is false. Okay, so going to number 6, right? Number 6 is just on this branch by itself. So to the bottom of this branch, right, we apply the rule for a false conjunction, and we would have to say false P and false Q. And we're done with that. But false P and Q is also on the branch that ends with number 8. So applying that rule to number 8, we get the same result. Right? So in this case, right, this one came from number 6, and this one came from number 8. So they look the same, but they came, right? We applied the rule twice. We applied the rule to one thing, and then we applied it to something else, right? What did we do? We added what the rule told us to the bottom of every branch that it's on. Number 6 is only on one branch, and number 8 is only on one branch. Okay. And now there's nothing complex left in the tree, so no more rules, nothing more to do. Now we examine each branch one by one. All right. Let the court case begin. All right. So, one branch. Any statements that are true and false on the branch? Yeah, P, right? So 3 says P is false, 5 says P is true. This bottom one, which I didn't number, also says P is false. So this branch is closed. All right, great. What about this one? The orange branch. Is there any statement that's both true and false on this branch?
Also
3 and 5.
Yeah, 3 and 5. Yeah. Okay, so these branches are closed. All right. What about lime green over here? Where is lime green? Here.
Q.
Q, right? So at the bottom we have false Q, and number 4 is true Q. Closed. All right. And last but not least, we have ice blue. Any statements that are both true and false on this branch?
Hold on, I'm confused.
Yeah.
How do we end up with the last lines being both false Q instead of false P and false Q?
Boom. Because I made a mistake.
Okay.
Excellent. Good spot. Ooh, my bad.
They're so good.
Okay. Does it change what happens? Fortunately, not. All right, so right, so this branch still closes, the green branch, right? Because we have false P and oh no, yes, and true P. Yeah. Okay. My mistake. Right. That's. Yep. Did I get it right the first time? Yeah, over here. That's even worse because I got it right the first time and then wrong the second time. Anyway, the moral of the story is, you got to pay attention. Like one, it's very detail oriented. Okay, and even the best of us make mistakes. Okay. And ice blue. Is it open or closed?
It's closed.
It's closed. Okay. Okay. Phew. So that was an easy save. All right. So all of the branches are closed. Right? Every branch has a contradiction on it. So when we assume that the premises are true and the conclusion is false, then every possible consequence of those assumptions leads us to a contradiction. Which means what?
It's valid.
That's right. It means that the argument is valid. This argument is valid because it cannot have true premises and a false conclusion. Right? When we try to give it true premises and a false conclusion, there's no way for us to make the case consistently. Every single way we try, every combination we try, gives us a contradiction, right? Something is both true and false. And so we can't have true premises and a false conclusion. That assumption fails, and the tree shows us that it fails. Every possible way, right, leads to a contradiction. And that's the beauty of the tree method. It goes through every possibility. And since every possibility fails, you can conclude that there is no possibility, right? It's because it's exhaustive. We find out like there's nothing we've overlooked, right? So if all branches are closed, then the argument is valid. Okay. All right, so this is a valid argument. If P then Q implies if P then P and Q. Okay, what do you know? All right. And let's do this last but not least. We had from, just being logged out of Blackboard, what? Stupid Blackboard. Okay, did that happen to you guys? Maybe you're not logged in. All right, I'm gonna do this from memory. So we had the argument we started with, right? If it doesn't rain soon, the crops will die. How was that? It went, if not then if it doesn't rain soon, the crops will die. If the crops die, then there will be no food for the winter. The crops will not die, therefore it will rain soon. Like that was the argument. Okay, so let's try it. Well, we have if not R, then D. If D, then not F. Not D. Therefore R. All right, and we say the premises are true, and the conclusion is false. All right, so that's how we start. Okay, we have a true conditional, we have another true conditional, and a true negation. So we have a choice of what to apply rules to. Now, it's helpful. So notice that sometimes some rules create new branches, and some rules just continue the branch that you're on. It's helpful, you don't have to, but it's helpful to always do something that doesn't branch before something that does. It'll make your trees shorter, or at least you'll have to write down less stuff, right? So it's a good rule of thumb. You don't have to stick to it. You can apply the rules in any order, and as long as you apply the rules correctly, you'll always get the same and the right answer. But to make things a little more efficient and a little easier, it's a good idea to apply rules that don't branch before rules that do, right? Because if you apply a rule that branches, you create two new branches, and then if you apply a rule that doesn't branch, you have to add stuff to the bottom of each branch. If you do the non-branching rule first, then it's common to anything that happens underneath it. So let's start with number 3, because that doesn't branch. So this is a true negation. All right, so false D. Right, so where does number 5 come from? Comes from number 3 by the false negation rule. By the true negation rule. So true negation, right? It's true that not D, so D is false. All right, that's where 5 comes from. All right, and now we have 1 and 2. Okay, they're both true conditionals. We have no choice except to branch, so fine. So let's start with number 2. Just why not? Just for fun. Okay, so from number 2 we get false D, and true, not F. So where does this come from? Comes from number 2. False D, true, not F. Okay? And I guess now let's do number 1. Why not? Okay, and now number 1 is common to both of these branches, 6 and 7. So from number 1, we get, right, we have to add to both of these branches. We get false, not R, and true D, false, not R, and true D. All right. And right, 6, 7, 8, 9, 10, 11. Okay. Anything else we can work on? So, all right, number 8. Well, this is a false, not R, false negation. So we can say that R is true. All right, so where did this one come from? It came from number 8. Nothing left to do on the branch that ends with 9. There's nothing complex on this branch. What about the branch that ends in number 10? Ooh, well, look, there's false, not R. So we can say that R is true. This came from number 10. What about 11? Okay, and now notice that number 7 is on both of these branches, right? So this is the last thing we have to apply a rule to. What do we get? We have, right, true, not X, tells us to write down false X. So what do we do with number 7?
It's false F.
Yep. But where do we write the false F? Right? Number 7 is on the branch that ends in 13, and it's on the branch that ends in 11. So we add false F, FF, to the bottom of this branch, and also to the bottom of this branch. Right? So where did this one come from? It came from 7. This one came from 7 as well. Right? You just add it to the bottom of each branch that it's on. Okay, and now there's nothing left on the tree. Nothing left to apply a rule to. So let's go one by one. All right, so we'll start with red. Open or closed?
It's closed.
It's closed, right? So we have a true R and a false R. So that's closed. All right, what about yellow?
It's closed as well.
Also closed, right? We have a true D and a false D. Okay. What about green? Do we have a statement that's both true and false?
R.
Ah, right. So 13 is true R, 4 is false R, so closed. And, oh no, we already did ice blue is the font. Right, we'll have whatever shade this is. This is dark blue. That's not very imaginative. Okay. Is there a contradiction on the blue branch? The dark blue branch.
B.
D, right? 11 is true. 5 is false. All right. Branches are closed. So, is it valid or invalid that there will be rain soon? Like, does the conclusion that there will be rain soon follow from these premises? Is the argument valid or invalid?
Valid.
It's valid. That's right. All of the branches are closed. Therefore, it's not possible for the premises to be true and the conclusion false. Therefore, it's valid. Yep. All right. So it's a bit of a rigmarole. There's no two ways about that. But other ways are even more of a rigmarole. Right? I mean, one thing is, you know, when you actually do a tree, it's helpful to like kind of lay, you know, take a piece of paper and give yourself a lot of room, lay things out as spaced out and neatly as you can to, you know, don't make it look quite the way I make it look, because, you know, one, my writing is not that great, but I also don't have that much space on this little tablet. But the thing about it is that as long as you apply the rules correctly in whatever order, you will always get an answer. Right? This is when you program a computer to figure out whether an argument is valid or invalid. This is how you do it, using these kinds of steps. This will always work. That's the nice thing about it. You know, there are a few certainties in life, and this is one of them. For what it's worth. Okay, any questions about this?
No, but I have a question about the midterm.
Yeah, sure.
So it's on, when is it again, the midterm?
We said the 2nd. So in a week and 3 days, 10 days. The 2nd of November.
And it's still online, right?
Yes. I have to think about how to put it together. There'll certainly be. I mean, the questions will be online for sure.
Okay.
I mean, you'll have them in front of you on Blackboard. Yeah. Whether. Yeah. Okay. I have to think about that.
Okay. No problem.
At the very worst, expect, right, that it's like walking in the class. You'll have the questions in front of you. You do it, and then you upload the answers, which may mean taking a picture of what you're writing down.
Okay.
As we would do in class, right? What's in it? I mean, everything we've done so far. But think of it this way: if you can take an argument, symbolize it, and then do a tree, you can do everything that's in the exam, right? Because everything we've done has built up to this. So if you can symbolize an argument and then apply the rules, right, to do a tree, that's it.
I feel like before the midterm that I'm gonna need a little more practice with this, because I feel like for a midterm to be coming already and we're just literally still learning this, it's a lot. You know, it's a lot of pressure.
I mean, that might be. However, we have been doing this for like, what, 2 weeks now?
Yeah, we have. I get that, but now you're teaching us different things where there's like 2 conditionals, and then there's 3 conditionals. Then we gotta add more branches onto those. So each time we come to class, you know, there's something new to being learned.
Well, no, it's the same thing, just being applied
Different
again
ways.
and again. I mean, we are practicing it, and like now we're at the end of. I mean, we've covered all the stuff we need to cover. Now we're just applying what we've learned, right? There are 8 rules, and you know, I mean, you don't use every rule in every argument. right? So I mean, this isn't. It may be new to you, but I mean, we have been doing this for a few weeks.
No, it's not new to me. Because I've been here. I know what we're doing. We've been doing it for the past few weeks. What I'm trying to say is like the stuff that we did today. Yeah, we've been learning the rules. We've been learning how to apply them in different, different situations, different arguments. But like, I guess what I'm trying to say is different arguments come about when we're learning how to apply the same rules that we've been learning. But it's each time it's a different argument. So that's what it takes some adjustment to get used to, when you're trying to apply the rules to different arguments when each time in a class, it's a new argument,
Sure, but I mean, that's kind of like, if this were like we were learning, some algebra, I mean, you couldn't say, well, okay, we had one problem and now we have another problem, and like that's kind of a new, that's a new thing. We're just using the same formulas applied to